see.
So it covers transistors to assembly to C.
Cool. Anyway, let's do it, and maybe they will watch it later. We will get. You can ask a lot of questions because there's only a few of you. So what I want to. All right. So the point will be, I don't think I made it super clear, these 4 fundamental subspaces the last time. I sort of confused myself and I was like describing it. So I'll try to like shed some more light on this, because that's really fundamental thing. Gilbert Frank calls it like the fundamental theorem of linear algebra. And essentially means to understand what are arbitrary rectangular matrices doing, how they work, how they operate. Oh, by the way, next week is the fall break, right? So that's Thursday and Friday off, right? So there'll be no recitation and no class on Friday, and consequently I'll be giving you no homework because it'll be weird to hand it out on Friday. I'm supposed to have a break. Okay. And the midterm, I told you, right? That's October 21st and 23rd. I posted on Piazza. Yeah. Oh yeah. Did you get the spline stuff mostly done? Some people were. Well, I guess we're talking to a very small part of the class.
Everything but the last one. Just because I hadn't spent time on it.
You mean the extra credit thing?
No, so the second time. The last for normal credit.
Oh, right.
Yeah, I haven't looked at it, so.
Okay. It should work. Some people got it figured out already.
The most painful part of it is trying to figure out how to plot everything. It's like the
I see.
Figuring out how that works.
Yeah, I know. Okay, let's try to figure out these subspaces. That's like the MATLAB stuff. I'm very confident you would figure it out sooner or later. But this stuff is like theoretical, but gives you like a very deep insight of actually what are matrices. That's I guess one of the main results of linear algebra. So this is like a precursor to the really biggest result, which is single value decomposition. But most of the critical ideas you will see already from these 4 fundamental subspaces. So actually, to give you the full picture, I need to start from orthogonal subspaces. So we talked about subspaces the last time, right? And the definition, I think you maybe even had it from Lifang. So I have 2 subspaces. Both are subspaces of some n-dimensional real linear space. And I said that they are orthogonal. This is a definition. So this is what I mean by this def thing. They are orthogonal if and only if for each vector v from V and for each vector W from the W vector space, guess what? They are orthogonal. Right? So this is my new notation for dot product. I also used to be writing it as this, like V dot W, but it just means a dot product. So it just means that they are orthogonal. So let's take a look at some examples. So in R2 I can pick one line. One line is a subspace, right? And if I want an orthogonal subspace, I just need to pick another. So this is if this is my V and this is my W, this is an example of orthogonal subspaces, right? Because any vector from here is orthogonal to any vector from there, right? All the vectors form this line, so this is fine. Now if I took 2 subspaces like this would be my V and this would be my W, and clearly those are not orthogonal subspaces, right? A 3D example. In 3D I could also like to take 2 lines, but in 3D I can also take an entire plane, for example like the XY plane, and if this is my 0, so I could say that the plane is my subspace V and this line is subspace W, and this is another example of orthogonal subspaces. In this case the V has dimension 2 and the W has dimension 1, right? So that's the idea. Now, in terms of matrices, remember we were talking about the null space of a matrix, right? That was all the x's such that AX is 0. and the row space. So the row space of the matrix was denoted as CAT because the row space is exactly the column space of A transpose, right? And there is an interesting thing to notice is that the subspaces NA and CAT are actually orthogonal. So this is an example. So let me write it like this: NA and CAT are orthogonal subspaces. Sometimes people write it for short just like this. This is like a symbol for two subspaces being orthogonal, this thingy here. And why is that? Why is that? It's relatively simple, right? Already from this equation, you can see that if X is in the null space, that means that AX is 0, which means nothing that every row of my matrix A is orthogonal to it, right? Because it means that A1, should give them the T's now, A1 TX is 0, and so on. All rows are orthogonal to X, and therefore any linear combination of the rows is also orthogonal to X, right? And that means that any vector from the row space of A, or equivalently from the column space of AT, is orthogonal to X. So for arbitrary vector from the null space, any vector in the row space, they are orthogonal. So this is true, and I can really write that this is true. There is also like an algebraic way you could say that, or algebraic argument. The idea is the same. It's just that the proof doesn't use this geometric dot producty intuition or the geometric reasoning, but just uses algebra. So if I pick any vector from CAT can be written as ATY for some y, right? And if I take an arbitrary X from the null space, then I need to show that X transpose ATY is 0, right? This is what I need to show, right? But this is simple because XT ATY is just AX transpose Y, right? And because X was from the null space, this is 0. So this clearly is 0. It's like funny to like see like two slightly different ways to prove the same thing. Either way, what we get is that the null space is orthogonal to the row space, which means that like intuitively, even though the matrix can be the null space, if my matrix is M by N, that means that the null space and the row space, they are both what? N-dimensional, right? Right, N-dimensional. So this picture, you can still imagine, it's the same sort of idea except that in N dimensions. I cannot really draw it or visualize it, but the idea is that if I pick one vector from one and the other from the other, they will be orthogonal. Now the same way I could also show that the left null space, the NAT, is orthogonal to the column space. Those were the four fundamental subspaces we discussed, right? This is the null space of A, this is the row space, this is the column space, and this is the left null space. So this is really the same thing except for A transpose, right? So I could prove it exactly the same way I proved it for A, except that I would take A transpose instead of A, right? Like, for example, imagine if I take X from the null space of A transpose, it means that A transpose X is 0, which means that X is orthogonal to every column of A, right? Because if those were the rows, if I transpose it, now I'm multiplying X with the columns of A, and it's orthogonal. I could also do this thing. It would be the same thing. Okay, so this is interesting, and it's even more interesting because I can say even more. They are not just orthogonal, they are orthogonal complements. So let's define orthogonal complement. I don't think It's just like a slightly stronger version of this statement, I can say. And this stronger version concerns orthogonal complement. So what is an orthogonal complement? So orthogonal complement of some subspace V, which is some subspace of R to N. And the orthogonal complement is denoted as V and this orthogonal symbol, and it consists of all vectors x from Rn, obviously, such that for each vector v from my subspace V, the V is orthogonal to x. So in other words, I pick all the vectors which are, equals 0, that's what I meant. I pick all the vectors which are orthogonal to the entire subspace, right? This essentially means being orthogonal to the entire subspace. So the only difference from like just an orthogonal subspace means the orthogonal complement is all the vectors that are orthogonal to a given subspace. So these examples I was giving before, like if I had in R2 like a line, then the orthogonal complement is exactly this line, right? All the vectors which are orthogonal to a subspace, they form a subspace also, and it's called the orthogonal complement, denoted like this. In again the 3D, so this was R2 example. If I have an R3 example, so if I have a plane, what do you think is the orthogonal complement of it? So if not really. If I'm in R3, I only have 3 dimensions, right? So the plane already takes 2 dimensions. It has basis like this, right?
It's a line.
It's exactly, it's sort of what I was drawing before. It's the line, right? If this is my 0, always has to pass through 0, right? Remember that subspace always has to go through 0. It's a linear subspace, and that's what it actually works the other way around too. So if I was in R3 and if I had my coordinates here and if my subspace was just this line, what would be the orthogonal complement to it? What do you think? All the vectors that are orthogonal to the line, right? So what are they? Yes, I get back the plane. And I think actually that this thing in general is true. If I take the complement of the complement, I get back the vector space. So the why I am saying this here is that not just that the null space and the row space would be orthogonal. This is what I said before. But it's actually true that they are orthogonal complements of each other. So if I take the null space of A and I make its orthogonal complement, I get exactly the row space. So this is like a stronger statement, right? And I would like you to understand why is it stronger. It's stronger because the orthogonal complement means there is nothing left, right? Like in 3D, I could have 2 orthogonal subspaces. In 3D, I can easily have 2 lines, right? And those are orthogonal subspaces, right? But if I take the orthogonal complement, it means that I complement it to the entire space. In other words, if I do the span of V and V or orthogonal complement, I get the entire space back. And this is important because this essentially tells me that there is nothing left here, right? So I guess that any vector now I can represent as a sum of a component in V and sum of a component in V orthogonal complement. Like I like this 3D example of this plane here and this thing. So if this is my subspace S and this is the orthogonal complement, if I have an arbitrary vector in 3D, I can write it as the component. So if this is my V, I can write it as the component in S, that's some Vs, and some or V1 and some component V2. So V1 is from S, V2 is from the orthogonal complement of S, and it's true that V is V1 plus V2. This is what I meant by this, the span of S and the S orthogonal complement gives me back the entire space. It's sort of like similar idea as a basis, right? Except that I don't like split it into the individual vectors, I just split it into two subspaces. I know it's sort of abstract, but that's what we have to do if you want to understand general n-dimensional spaces. Does that make sense? Cool. So now the four fundamental subspaces will hopefully also make sense. So the four fundamental subspaces are these four subspaces associated with an arbitrary rectangular m by n matrix, right? So this is m by n matrix A, which happens to have rank R, right? You know that R has to be less than or equal than minimum from m and n. And what the matrix A is doing, the matrix is nothing but a mapping from, or representing a mapping from Rn to Rm, right? Because matrix vector multiplication takes an n vector and maps it into an m vector, right? So what we have in this diagram here to the left is the R to n space, and here we have the Rm space. And the matrix A performs this mapping. This is my A. It goes from Rn to Rm, right? A transpose, it does the opposite mapping, right? It goes from Rm to Rn. So it goes this way. A transpose. And this is how I can decompose the R to n space. So this is my inputs to the mapping. This is my outputs. And the point of this four fundamental subspaces diagram is that here the space R to n decomposes into two orthogonal subspaces, such that one is the orthogonal complement of the other. So the first one is the null space. Those are all the vectors x such that ax is 0. And the orthogonal complement of NA, as I was just describing, is exactly the row space. So the CAT is the row space of the matrix A, or equivalent the column space of AT. Right? You can always look at it two ways. And as I described in the very beginning, these things are really perpendicular. So if I take any vector from here, it's orthogonal to any vector from here. In the row space, that's what we discussed before, has dimension R, that's the rank. And the null space, now, because it's orthogonal complement, it has to have dimension n minus R, right? Because if I sum these things together, I have to get back the dimension n. That's the dimension of the space where I started. Okay? And the same thing happens on the right side of the diagram. Here I'm just decomposing the m-dimensional space. So that's the space where the matrix A maps to, or AT maps from. You can like always look at all these things like in two different ways. And the null space here is the left null space. So that's the space of all vectors y such that ATY is 0, right? It's also equivalent to saying that YTA is 0. That's why it's called the left null space, because on the original matrix A, I'm acting from the left, and I'm asking what vectors multiplying A from the left as rows will give me zeros. That's the left null space. And the column space is just the linear span of all the columns, right? And the column space, as we can prove from the reduced row echelon form, has also dimension R, where R is the rank. So the dimensions of both the row space and column space are equal. They are equal to R, they are equal to the rank. Now, I did not do the proof super rigorously, or maybe I didn't do the proof at all, because I think it will be even clearer later on from singular value decomposition theorem. So that's essentially a stronger version of this. But let me first finish this discussion. Here on the right side, in the Rm space, the same thing happens. The column space is the orthogonal complement of the left null space and the other way around. So if I take any vector in Rm, I can uniquely decompose it into a part in the left null space and in the part in the column space. So how exactly the mapping A works? So the matrix, if I do some AX, so that sends me an n-dimensional vector into an m-dimensional vector, right? So X was arbitrary vector in R to n, and the result AX has to be, of course, in the column space of A, right? Because all this is doing is just a linear combination of the columns, right? So no matter which vector from here I pick, I end up somewhere in here in the column space, right? So this is one useful thing you can learn from this, or you can remember using this diagram. So the mapping, wherever it goes to the column space. Now, we can say even more. If the vector happens to be from the null space, it goes exactly to the origin. Here this thing where these things intersect, those are origins, those are the zero vectors. So in other words, if I have an arbitrary vector here, I can split it into two components, into a component in the null space, let's call it, I don't know, xn, and into a component in the row space, let's call it xr. Now the component in the null space maps to 0, and the component, so this was arbitrary vector, the component in the row space, it maps somewhere into the column space. Now the same way it works the other way around, except that now we are looking at matrix AT. The matrix AT, again, all the arguments are just reversed. It maps to the column space of AT, of course. So it has to map only here. And the vectors that are here are being mapped to 0. And the vectors that are here are mapped to the row space, to non-zero vectors in the row space. So I suppose the most important thing to remember is that in every rectangular m by n matrix with rank R, there is an R by R non-singular matrix hiding in there, right? That's essentially like this mapping between the row space and the column space. And these null spaces are these guys that map to zeros. One is going the forward mapping using A, and the other one is the backward one using AT. So this is essentially what happens in arbitrary rectangular matrix. It's just that it's like all hashed together, so you don't immediately see it until you do the reduced row echelon or even SVD. But it's true for any matrix. So all you need to do to understand it is to figure out what are the null spaces of A and AT, and then the rest will be just a mapping, which will now be invertible between these two. And those are the things why it was not invertible. Those are sort of the zeros. Sometimes they are the troublemakers. So I want to nail this point home. So I will actually show this on the example we discussed before. So I just want to show you how this works on one particular matrix. So this is the matrix we are working with before. 0, 0, 0, 1, 2. I sort of always like better things with some concrete numbers where it's a little better to imagine. So this is my matrix A. It's a 5 by 3, 3 by 5 matrix, right? Three rows, 5 columns. So it's a mapping between R5 and R3, where A goes from R5 to R3, and A transpose goes from R3 to R5, right? So if this is my row space of A, then the last time I found the basis vectors for the row space, and these are, because this already is in reduced row echelon form, then it's simple. Then the row space is just these two basis vectors. So it has dimension 2, which is the rank, right? The R is 2. Always has to have the dimension equal to the rank. Here is my 0 vector, and here is the null space. So the last time I showed you that the null space is spanned by this basis, or is generated by these basis vectors, -5, 0, 1, 0, 0. 7, 0, 0, -2, and 1. And the dimension of the null space has to be 5 minus 3, which, 5 minus 2, which is 3, right? It's going from R5, and 2 are taken by the rank, so this is a 3-dimensional space. Now what happens in the image? So here I have my column space, and in the column space I have this basis. Again, dimension is 2, right? And now the left null space is, how many dimensions does it have? So here I'm decomposing R5, and here R3, right? So this has to have dimension 1, because it's 3 minus 2 is 1, and the basis of the left null space is 0, 0, 1 vector. And you can verify that like any of these vectors is orthogonal to any of these vectors, and same here. Here it's trivial, right? 0, 0, 1 is obviously orthogonal to these two vectors. And you can also verify that if I take any vector from here, if I take a linear combination of these vectors, it will go to 0. So this is my 0 here, this is 0 here. This is 0 in R5, so this is 5 zeros. This is 0 in R3, so this is 3 zeros. So this goes to 0 via A. The same way this goes via AT. So if you look at it, if you take AT and multiply by 0, 0, 1, you always have to go to 0, right? And any vector from the row space multiplied by A will go to a non-zero vector in the column space. The same way, any vector in the column space multiplied by AT will go to a non-zero vector in the row space. So that's this picture, and basically big part of the remainder of the course will be building up the theory towards singular value decomposition, the SVD, which SVD is essentially a stronger version of this, which tells you that you can pick the bases in all these spaces in a special way, such that the matrix essentially reduces to a diagonal matrix. It's just like a very, very, very powerful thing, being able to reduce arbitrary rectangle matrix to a diagonal matrix, because it's like a sledgehammer in linear algebra. Like almost all problems become trivial once you have this single value decomposition. So this is the precursor of SVD, which you can get already from elimination. It's cool. So it's cool because it like requires much simpler mathematics. Okay, so I think I hope I described the 4 fundamental subspaces. Here is just like a little summary. I don't think we need to go over it again. So those are the 4 fundamental subspaces. They have these dimensions. They are orthogonal complements in Rm and Rn. I think I described this completely by now. So as I said, the big part of the remainder of the course will be building up to SVD and doing applications of SVD. And the first part of this is orthogonality. So I think I mentioned that the basis in SVD will be essentially the basis of these subspaces, but that they will be orthogonal. So we first need to describe what are orthogonal or orthonormal bases. There's not a huge difference between orthogonal and orthonormal. The only difference is that with this normal, you also mean that the vectors are unit and orthogonal. So don't let that confuse you. So when I was this is a funny thing. So when I was talking about bases, I said there is like no shortage of bases in linear spaces, right? There is plenty of bases. Like if I have R2, for example, these two vectors are a perfectly valid basis, right? They span the entire space. They are linearly independent. That's how basis vectors are defined, right? The problem is that if I want to like find a coordinate of some vector with respect to these two guys, it's not so nice because I need to invert some non-trivial matrix. So these bases are not as nice as the case of orthonormal bases, which essentially correspond to the case when these two basis vectors are orthogonal vectors. So that's exactly what's captured by this definition. So orthonormal basis, by definition, is a basis such that all vectors are mutually orthogonal and have unit length. If I said orthogonal basis, then I mean just this part, and they don't necessarily have to be unit length. Oh, by the way, so basis, what basis wants from the vectors is first linear independence, and second generating the entire space, right? The interesting thing is once I assume orthogonality, once I say that these vectors are orthogonal, this is what it's saying, right? For every I and j, the dot product of ui and uj is 0. That means that they are orthogonal. So once I assume they are orthogonal, it follows immediately that they are linearly independent. It's very easy to prove. To prove that, all I need to prove, so if I want to prove that vectors u1 to un are linearly independent, that means that I need to prove that the only sum that gives me 0 is the trivial one, right? So how do I prove this if I know that all my vectors u are orthogonal? So if I take this equation, and now I assume that or let's do k, doesn't have to be the entire space, to alpha k u k is 0. So let's assume I have k orthogonal vectors u, and I take an arbitrary combination, and I say that this has to be equal 0, and I need to prove from this that all the alpha i's have to be 0 for this to be true. And if they are orthogonal, it's sort of simple because all I need to do is do a dot product, dot it with all the ui's, right? So if I dot it with u1, I get alpha 1, 1, and all the other ones go away because they are orthogonal, right? u2, like for example, like u2, u1 is 0, right? So that this immediately tells me that alpha 1 is 0. The same argument goes for the other alphas, right? Then I dot product it with u2, and I get that alpha 2 is 0. So this is exactly what happens here. So if I have orthogonal vectors are automatically linearly independent. In a sense, orthogonality is asking more, right? If in the R2 example I draw here, linear independence, all it wanted from the vectors do not be on the same line. Right? So the moment they are like a little bit apart, they are linearly independent. Orthogonality in R2 wants more. It wants them to be like this. It wants them to have right angle. So that's intuitively a stronger requirement. Okay? So orthonormal basis, you might be expecting anticipating what's coming. Orthonormal matrices. If I take all my basis vectors and put them in a matrix, it's one of my favorite things to do, then I get the matrix which is called an orthonormal matrix. So matrix is called, and can be arbitrary rectangle matrix. Notice that here is n by n. And a matrix is called orthonormal if the columns form an orthonormal basis. Right? So if I take all the columns then and take the dot product of any two column vectors, I get 0. And the beauty of matrices is that all these funny index conditions where I had to be saying ui t u j is 0 for each I and for each j, and then I should even specify where I goes from and where j goes from. Instead, I can beautifully say it in matrices just by saying QTQ is identity. That's equivalent to saying that all the columns are mutually orthogonal. Why is that? Let's take a look. So if this is my Q, this is my Q matrix, then my QT looks like this, right? And if I do QTQ, what does it mean? So in QT, the columns of Q have become rows, right? So the QTQ is nothing but computing all the dot products between all the columns of Q. The columns is the key thing, right? So if I say that this is identity, oh, sorry. No, it's wait. Yeah, it's correct. This size item has to be the small one. There's just only one thing you can get wrong. So you have like 50% chances of being right, but it's like important not just to guess, right? It's the small identity. And the identity, it's saying exactly this, right? It's saying that if I is equal to j, so this is actually, see what I wrote here is actually not true, right? For each I and for each j. Because I should have written for each I not equal to j, right? The point is that if I happens to be j, then I have ui with ui, and that has to be 1 if they are orthonormal. If they are not orthonormal but just orthogonal, this doesn't have to be 1 but has to be non-zero. And this is exactly what the slide says, that the entries correspond exactly to the inner products. Yeah, I think you should now be able to like write down, I don't have to do it, what these inner products are, right? If like numbered it would be like, this would be like u1.u1, u2.u1, and so on. So the orthonormal matrices are incredibly useful. The best thing is that inverse becomes trivial. So if I have a square matrix, why need a square matrix? Because I can only talk about inverse of a square matrix, right? Of a general rectangle matrix that does not have any inverse. We will have a pseudo-inverse, but no inverse for rectangular matrices. But if it happens to be square and orthonormal, then the inverse is exactly just transposition. That follows right from here, right? If it's a square matrix, then inverse is defined, and the inverse is just the matrix which, if I multiply it with, I get identity. And in the special case of orthonormal matrices, that matrix is just the transposition. So that's very cool, because if I have an equation like this, if I have to solve qx equals b, all I need to do is multiply it with qt from the left, right? Then qtq, then I get this. But this is identity, which is beautiful because this is already the solution. That's why orthonormal matrices are so important, because they really simplify, and that's also consequently why SVD is so important, right? Because it gives you orthonormal matrices for both the source space and the target space of the matrix for both my Rn and Rm, making all things much easier. Oh, by the way, this works even if it was not square. Just that the x and b would have to be of appropriate dimensions. I can still do it, right? I can still multiply by qt and still has to be identical. Another cool property of orthonormal matrices, and it is that they preserve the Euclidean norm. So if I have a vector y and I transform it by an orthonormal matrix Q, then I get some vector x. And if I assume they are squared, that both x and y are in the same vector space Rn. And what I'm saying is that the norm of x squared is the norm, or even without these squares, right? The length of x is equal to the length of y. And to prove this, it's very easy. The proof is here. Then the squared norm of x is just x dx, right? The dot product of x of itself. And if x is the q times y, then this is just qy transpose qy. But because of how transposition works, I can write it as y transpose qy. But I know that qtq, that's the whole trick, is identity, because q was orthonormal. So this is just identity, and identity I don't even have to write there, because identity just returns the vector back. So this is just yty, right? So it means that the length of x is equal to length of y. Geometrically, it means that orthonormal matrices don't change the length of vectors they are operating on. And this might give you an idea what is the geometric interpretation of orthonormal matrices. What other matrices are preserving the length of vectors? By the way, they are also preserving the angles, right? That the same way I could prove that the dot product of x and y does not change if I apply q to both of them, right? Qx and qy, right? Because again, exactly the same way, these q's just cancel. And yeah, this is x dy. So I start from here. I transform both x and y by q. And I notice that the dot product of the qx and qy is the same as the dot product of x and y. So they preserve both the lengths and the angles. So what are those geometrically? We have seen transformations like this before, right? What does it mean? Huh? Yeah, that's correct. But not just rotations. There is a little trick to it. So it is true that all rotations are orthonormal matrices. And the cool thing is that now we don't have rotations just in 2D or 3D. Orthonormal matrices are a way to reason about rotations in arbitrary dimension space, which I think is sort of cool, because it's something you probably cannot imagine. If you have like 100-dimensional space, what does it mean to rotate it? But you can express it using an orthonormal matrix, and you can compute with it. And it actually has, it's not just like a mathematical curiosity, it has very real applications, which I will describe next. But let me first finish this little,
Linear transformations?
So linear transformations, they don't necessarily preserve lengths, right?
Oh, I guess not.
Because you can have scale there,
Right,
so
yeah.
they can squish it. So it is true that, correct. So let me just finish this. It is true that all orthonormal matrices, of course, are linear transformations, right? Because all matrices represent linear transformations.
Okay. Yeah.
But not the other way around. It's like a hierarchy, but reflections, exactly. Reflections are not rotations, so those are like the mirror transformations. Those are like funny, right? Like if I have like a mirror here, then if I have like a vector, then it gets mirrored to the other side, like this. The funny thing is that the reflections also preserve lengths, but they don't have. They are like not realizable in the real world, right? I mean, if I have a rigid object like something, or like the pen, then I can certainly rotate it, but I cannot really reflect it unless I have some superpower. Okay, the application, or one possible application of the idea of like rotating in n-dimensional Euclidean space or orthonormal matrices is transform coding. I think I will just start it now and finish it on Monday. This is essentially leveraging the fact that the inverse of an orthonormal matrix is such a simple thing, that it's just the transposition. So it's very easy to apply the transformation and its inverse, the transformation going back. And the idea of transform coding, which is the basic idea of JPEG and most other compression methods, is to apply a well-chosen rotation or orthonormal matrix Q. And this will be chosen in a smart way, such that the signal decomposes into, for example, in JPEG, into some high frequency parts and low frequency parts. And you can safely discard the high frequency parts, because in an image those are typically just noise, which you often don't want in the image in the first place. Now I'm simplifying things quite a bit, but I will explain it better on Monday. All right? Any questions? Okay. Thank you.